welcome to this week's episode of Automated. I, of course, am Stefan Zoxmacher, talking to you from our global headquarters in the Mission Street, just by the RV that someone lives out of.
I swear to God, if you mention what I'm wearing one more time.
It's also exclusively where Ilia shops for new clothing. Sitting across from me is a gentleman who just handed a wad of cash to someone in an RV in the Mission. Sir, who are you?
That's our new localization provider. Every time we get to that particular street, he just starts to shout, and then we know we're at that particular street.
We do dead reckoning off of crazy people shouting in the street.
Yeah,
which is actually a fairly reliable system.
Only in San Francisco.
Our topic of discussion today is going to be localization in hybrid environments. We're going from places where you might have GPS to not, or in our case, going from places where you can hear a certain homeless person shouting or can't. So, I mean, I think it's apropos, as some might say.
Definitely.
So this again
I feel like this could be one of those fodder episodes for right-wing news outlets. Look at the downfall of San Francisco.
Oh, yeah, naturally. So this is our podcast, Automated. We do this podcast to talk about robots that we love, that we hate, how we build them, how we abuse them, and sometimes things that we learn along the way. We do this podcast in two segments. In the first, we kind of make up a robot based on a randomly drawn piece of technology, another randomly drawn business case. And then we talk through our subject, which today is going to be hybrid localization, when you're in environments that sometimes has great GPS, sometimes has no GPS. And the real fun part, which is that special little place in the middle where you don't know if you have great GPS, bad GPS, spoof GPS, kind of fake GPS, kind of in and out GPS, and you still have to somehow drive where you need to go. So that's what we're going to talk about. This is Automated, and let's play our little game, Ilia. What business are we starting today?
All right, off to the races. So I picked this card here, and it is trains.
Trains. I actually just saw a train thing that I was very excited about. I got a weird inbound from some investment banker for autonomous electric trains to move trucks around, which just sounds like, a train.
I was going to say.
and somehow their speed of delivery was really fast. I want to do a cool one for trains. Actually, I think let's just talk about autonomous trains. It's not going to be fun.
No, we need a bizarro tech.
Yeah, we need a bizarro tech.
What do you got at the top of your pile there? Stefan is entirely not randomly sorting.
Yeah.
He is applying creative decision-making here.
Yeah, I'm using lots of creative decision. Let's talk about LiDARs and trains.
LiDARs and trains?
Yeah, I just want to talk about train autonomy in a more serious context, because people love saying, hey, robo-taxis are a whole thing, self-driving trucks are a whole thing. You know what we're going to have first? We're going to have autonomous trains.
Yeah.
And trains are a funny thing. When I was first starting my self-driving truck company, Starsky, I followed this thread in something like 2005, 2007, 2003, whatever. There was a rather horrific train accident where 10, 12 people died. And I say that both seriously and somewhat sarcastically, because a bigger accident than that happens on public roads every month. There's a 50-person accident. But regardless, this led to national action for a standard called PTC, or positive train control. And positive train control is essentially adaptive cruise control for trains. So they can see objects before the human operator can. They can start to slow down smoothly. The government allocated, I want to say, I haven't read about this in 8 years. I want to say $10 billion for PTC, with a 10-year time horizon to get it deployed in American trains. And as of whenever I was reading this, 2016, 2017, the only real progress had been an announcement that the PTC project was going to be delayed.
Yeah. Can you tell Stefan's going to be the dad who has model train set downstairs?
I have a model train set.
So many train facts. No, but seriously, the problem, I'm predicting a problem here, because I've not heard about this program.
Yeah.
But I'm predicting a problem here. The kind of trains that you'd care about, so mostly freight trains, because that's most of railroad.
And actually, as a fun fact, America has a bigger and better rail network than Europe. The thing is, in America,
it's entirely freight.
Business is numero uno.
Yeah.
Screw those loser people. If they were worth more money, they'd be billion-dollar corporations. So we actually prioritize freight traffic over
human traffic.
So humans sit on the siding while a bunch of lettuce goes by.
Yeah, I'm sure lettuce goes by train and not oil. John Oliver did an episode on this just last weekend about trains. But anyway, I'm predicting the problem here.
Us and John Oliver, we're the big two.
Oh, yeah, of course. Who else do you get news from? The main issue here is the stopping distance for a large freight train is a mile.
Literally, the PTC program was going to have sensors spread around.
Yeah.
And like they just couldn't make progress on like the software framework.
Well, it's just like your stopping distance is so ludicrous.
Yep.
That there is no LiDAR you can mount on the train that would see far enough to matter.
A friend from the autonomous trucking world recently reminded me that Shoe Simple once made a claim that they had a LiDAR that could work that at costs that made sense for a self-driving truck could work to give you a range of 1 kilometer on a LiDAR. They made this claim at some point, let's say in 2019. Yeah. No one ever heard about this LiDAR again. It was never shown, but like, let's say it exists.
Yeah.
And let's say you can like 10x its budget to try to get, 3 kilometers of range.
I believe Too Simple. They made the good decision to leave the American market entirely.
After the founders fled because of, financial irregularities.
Seem legit. No, actually, I've actually worked with a LiDAR that could see on the order of that range. Yep. It was an enormous laser cannon that we had to mount on a small car to be able to use.
An alternative is you just put a LiDAR along the train tracks every, 300 meters.
Yeah. The point being like, even 1 kilometer is not going to be enough for a stopping distance of a serious freight train.
Yep.
Just because you have so much mass, doesn't matter how good your brakes are.
Yep.
So you'd probably be looking at some sort of distributed sensor network.
Yeah.
Yeah.
We just got the 3-minute warning and we're going way too serious for this one. I think we need to radically change the direction of what we're doing with trains.
So what we do is the front of the train has a ranging LiDAR.
Massive ranging LiDAR.
To target the laser cannon, which is of course chemically powered, as we discussed before. So that it knows exactly what to blast off the tracks.
I think part of the problem here is that people are generally okay with trains hitting you. Like just speaking frankly, we've all come to expect that if you step in front of a train, it's not good for you.
Yes.
So the expectations of obstacle detection for trains are incredibly low. So then the question remains, why do you have a human on the train if like subway systems can be autonomous? And like outside of you need someone to deal with a bunch of weird subsystems that are quasi-mechanical, it's hard to come up with an answer.
I think trains are not.
Which is probably the same conclusion the railroads came to, which is why they only have like 1 person per train.
It's 2. They're trying to do 1 now.
We just got the 2-minute warning. Let's pivot into less serious trains.
Yeah, well, I was going to say that, one last comment here. I doubt actually hitting stuff causes most derailments.
Yep.
Most derailments are caused due to failure of the brakes of a particular unit or taking a curve too quickly or track maintenance. Like it's pedestrian issues like that. Actually hitting stuff probably makes up tiny minority of derailments.
Well, okay. Along with my pivoting, how about this? Let's make a whole new train network, rail network. Step 1.
Yeah.
I'm thinking small trains, like the size of a standard Amazon package.
Okay.
Robots to lay tracks through HVAC systems and sewers.
Are we getting back to our sewer delivery idea? Wasn't this like
all roads go back to sewer delivery robots. And you basically have a rail network within a city that can move a standard Amazon package anywhere in the city within 45 minutes.
Even better.
Yeah.
Instead of these large train, large freight trains, you have a smaller system that carries individual carriages. That are electrically powered.
That was the slide deck that I saw earlier.
I'm getting to this. I'm getting to this. Don't spoil the surprise.
Did you look at this one?
No.
I didn't share this with you.
Basic physics is instead of the efficiency of a large locomotive, we're going to have 1 million tiny little failable systems, each with 1/10 of the efficiency.
I swear. So I saw, I'm going to wrap it up. I'm not going to name the company because that feels too mean. But I saw on an investment banker's website, because I was looking for relevant robots to see if like there's anyone who could say that they're real or not, a train where the locomotive looked like the Tesla Semi.
Yep.
It only pulled a single carriage, which had a truck parked on it. And it claimed to deliver stuff cross country in 1/5 the time of a regular train. Maybe because it doesn't stop.
I mean, I think
so. It also has an infinite electric battery.
Yeah, infinite battery plus, the minor problem of train rail scheduling, which actually is what causes time problems. A straight shot is going to be pretty damn fast. That's not the problem.
Well, I don't think we invented a robot here. I think we came close to talking about trains because neither of us have ever gotten a chance to talk about trains before. And we nerded out for real as opposed to making up a silly thing. And when we made up a silly thing, we got awfully close to making fun of, what I assume is a real startup with real people who believe in it, which is not the move I want to be doing.
I mean, Hyperloop existed.
And with that, Let's change subjects a little bit. So, Ilia, compounding a handful of conversations we've had, we got a customer or a potential customer or someone who likes robots. They want to drive from inside of a warehouse to the yard and then back in.
Mm-hmm.
Or maybe they want to drive from one field through a tunnel into another field. Or maybe they want to drive from one field through, dense forest while the Russians are deactivating and spoofing GPS and then into another empty field. How do we do it?
Magic.
And if you want that magic, listener, you too can be a Polymath Robotics customer. Just wire your entire bank account to our bank right now.
In fact, just send us your social security number.
We might even send you those spray foam leads that we got paying for earlier. We got an inbound for dark. 50 leads for all the best spray foam providers in San Francisco, which is a lead list that I need.
Super relevant.
Yeah.
Super relevant. Thank you, marketing team. But no, so main
how do I drive
here,
through this tunnel?
Yeah. So stepping back a bit, the real question that we face over and over across our different robots is, how do you know where you are relative to somewhere on Earth?
Yeah.
Which generally people use latitude, longitude for, or UTM or ECF or any of these others. But some agreed upon grid pattern.
I imagine robotics and localization is hard if you're a flat earther.
No, it's much easier. A plane.
Not
perfect.
If the robots need to get somewhere.
Well, it's always a plane. Just make the planar approximation. It's perfect. Don't worry about your declination or anything. That doesn't exist. So the real challenge becomes if you're in a building, for example, like a home robot, you have a very good understanding of the boundaries of the world, or relatively good. And so you only really need to localize relative to those boundaries. And if you're outside, you have a very good understanding of, I'm here, latitude, longitude, because of GPS or because of some other localization system. The trouble becomes when you have to put those two together. So to put it in context for folks, if you ever use that Google Maps feature where you can see streets and then you see a building and you can look at different floors of the building and what like the floor plan of a mall is.
I've never seen that feature.
Yeah, it's really fun.
Maybe because I'm on the Apple side now. They stopped showing me these things.
It's just, you'll get it in a few years. It'll be revolutionary. Doing that matchup of floor plan and layers to the Google Maps trick is fairly difficult. And Google actually came up with a whole software package called Cartographer.
Really?
To help do indoor localization, in part for building these maps.
Huh.
So you can check out Ross Cartographer. Originally, it was just a guy walking around with a LiDAR and a backpack with some storage in it and compute.
I saw him. I tried taking his lunch money.
I mean, mean. Rude. But yeah, building up these maps and then referring them to actual location in space is non-trivial.
Yeah.
And so what most groups end up having to do is having to have a localization system which can switch what coordinate frame it's using depending on what situation it's in.
Yeah.
Is using something like latitude, longitude outside and something like relative position to some map frame.
But what about when you're exiting the tunnel? What about when you enter into the building? Do you just snap to that other coordinate frame?
Yeah. And that snapping in particular is difficult. So the way that there's a raw standard, there's a few raw standards that are quite like REP 103, 105, doesn't matter. But the main part about that is they define the world. Yes, every listener has heard of these, I'm sure.
Yes, naturally.
Stefan's making a face at me.
I actually have them tattooed on my chest.
I mean, I'm certain of it.
Right there with ISO 26262.
Yeah.
And so, which I sometimes, but like I a bad tattoo artist, so he wrote ISO 2626262626262.
That's the banana problem. It's okay. You'll have to get it laser removed and re-tattoo UL 4600 in its face. But that's a future problem. So
how do you snap to the new coordinate frame?
Right. So the raw standard and the standard way generally to do this is you have one coordinate frame called map, which is your global location, and one frame called odometry or ODOM or local, which is relative to that global frame. Where are you in space? And the way that you do that is your map frame is accurate but discontinuous, so it can have these snaps. And your local frame is less accurate but smooth.
Mm-hmm.
The reason you got to be worried about these snaps is imagine your obstacle detection layer is doing some processing.
Yep.
And it's detecting something that's 5 meters away.
Yep.
And then you exit the tunnel, you regain GPS, and suddenly your location snaps forward by 3 meters. Now your obstacle detection thinks it's only 2 meters away.
Yep.
And now it thinks that there's a security or safety risk.
And especially if you just move forward 3 meters in a millionth of a second.
Right.
Which would be fast.
So you can do these kind of filtering steps, but any filtering you do inherently introduces latency or lag. There's very advanced filtering methods you could do to reduce that. But fundamentally, it's a trick of wait for more readings to get a better idea where you are, which means you're waiting some amount of time. So there is definitely some challenges.
You did something like this at ClearPath, right?
Yeah, I mean, basically any robot you have will have to have some way to kind of square the circle of its global localization and its local localization.
Mm-hmm. So something that we saw recently is we were working with someone who should be good at GPS, and and essentially the thought was maybe our GPS can just get us all the way there if we only drive in places with good GPS.
Yeah.
And that was theoretically they always have open sky above them. Why isn't that working the way that they thought?
Yeah. So even it's funny, actually, just today we were testing out a new GPS here at Polymath.
Yep.
We had a GNSS solution.
We had a great autonomous vehicle. It was a push cart with 2 robotics engineers pushing it around the block.
Yeah.
So 2 engineers to 1 robot. It's actually not that bad.
So hey, Cruise would be jealous.
Jeez.
So basically, even walking around relatively not that skyscrapery San Francisco, which is nothing like Manhattan, for example.
Yep. For reference, our neighborhood is like 3 stories tall.
Yeah. Maybe 4. Let's call it. You're still having a lot of problems with GPS shadowing, where the buildings are blocking the direct view of the satellites. And so the accuracy of your solution goes down.
I mean, I guess like at what angle of the sky do things block the satellites? Because I mean, like the Trimble constellation, for example, how many of them are generally above the horizon right now above me?
You can't really answer that because the GPS or GLONASS or any of these satellites are in medium to low Earth orbit.
Yeah.
So they're constantly actually flying around.
Yep.
So you don't actually have a stationary point you can point at.
Well, yeah, but I guess my point is like, is the constellation big enough that there's always one kind of directly overhead, or
maybe there's not an infinite amount of these things.
Yeah.
The other trick though is just 1 is not enough. You need to have 3 at the theoretical minimum. Practically, you need to have 6 to 8 to have a decent lock.
So
and the
then
chance
having
of 6 to 8
directly above you
is very low.
How many satellites are in orbit? Ish 1,000?
No.
100?
No more localization type.
Yeah.
Probably low 100 if I had to guess.
Okay.
Maybe like 50 GPS. I don't know exactly. I'm probably lying, but like low 50 GPS, maybe low 20s of the European standard.
So that essentially, if you're driving in between 2 4-story buildings with, a single lane each way street and a sidewalk that's a decent enough size, you're probably only going to have a satellite directly overhead, a satellite less than 25% of the time, and 3 satellites less than 5% of the time. Just the way that geometry works.
Yeah, exactly.
And I failed geometry the first time, so it might be that how you divide up a sphere is different than I think. But.
Yeah, even assuming there's 500 of these localization satellites, you're still just probability wise, you're not going to see very many of them.
So if you're driving into a pit, that pit can't be very deep for you to have GPS.
Yeah. And there's even a more interesting problem where just getting blocked is bad enough, but then you actually get multipath behavior. So what will happen is the radio waves coming from the satellite will bounce off a structure like a building or a bridge or whatever, and then hit you from another direction.
Yep.
And so now you've gotten this extra bounce in terms of distance calculation, because all localization or GNSS computer is doing is it's picking up the signature from each of these satellites, which has a very accurate clock, and determining how long that signal took to get there. And so it's triangulation. I know where the satellite was.
This time. Here's some straightforward math. Here's my distance between those 3 points.
Straightforward-ish. You actually have to take. You have to take
straightforward that I can't do, but that
No, really.
Almost everyone on our team could do.
Fun side note. You actually have to take into account special and general relativity to get GPS to work. Yeah. It's accurate enough.
Listen, I'm a Newtonian physics guy. Yeah. I don't believe in anything afterwards.
That gravity plays a role in the accuracy of your GNSS. Jeez. Not only gravity, atmospheric conditions. So hot pockets or cold pockets or weather plays an role in your accuracy of GNSS. Which is why even real-time kinematic corrections or RTK is even a thing. Yeah. Because the whole trick of RTK is you just sit a receiver for a long time, get a baseline, and then subtract out that error from your active reading. So it's not trivial at all. I would not be able to write it for sure. Okay. Not easily. Anyway, if you have these signals reflecting off of objects, suddenly your distance is that much further.
Yeah.
And so now you're
and also like it goes to say that people can think they're good at GPS when that GPS needs to give you here's where you are.
Yeah, like 10 meters.
And then it can do nothing valuable in the actual localization landscape.
Yeah. Your average cell phone looks like it's really accurate, or your car navigation when you're driving. But then you think about it, and it's really plus or minus 10 meters or so.
Yep.
Which for a robot is functionally useless.
Insufficient.
Not just insufficient. Like, I cannot think of a robot that would be happy with plus or minus 10 meters accuracy.
A cargo ship.
Yeah, not in port.
All right, so let's talk about like what happens if the GPS gets spoofed.
Yeah, well, not only spoofing.
Like, what's the spoofing actually look like?
Yeah, and not only spoofing. The other thing to consider is most GNSS sensors will not output the error that they are actually collecting. We have had to find really good manufacturers who actually output covariance, which basically just means the error that the sensor thinks it's getting.
Yep.
Because if you just have a reading, you have no idea how accurate that reading is.
And the reading right now might be, give or take 10 meters. The next reading might be give or take a meter. The next one might be give or take 40 centimeters. And then it might be a whole sub 5 centimeters.
Yeah.
Yeah.
Exactly. And so how you fuse that into your localization is non-trivial.
Yep.
That is even before you get to the topic of spoofing, which has become a very interesting challenge, particularly in military situations, but in general.
Functionally, how do you spoof a GPS?
So you can
knowing that we're on time before I have to be on.
Yeah. So the you can do two things. You can jam it, which is basically you fill the radio waves with noise, and it just can't see any satellite. Or you can pretend to be a satellite by sending those encoded transmissions.
Those schmucks.
The most low rent way you can do it that most GNSS would filter out, but not all, is you have a GPS receiver, you receive the signal, and then you send the same signal time delayed by a microsecond or two.
That's fantastic.
And suddenly it's getting two readings that are slightly different.
Yep.
And suddenly your accuracy has gone out the window. Right. There's a bunch of companies that specialize in filtering out this kind of noise, but it's a very hard problem and there's no global solution to it.
So let's say you're driving through a forest and you have variable GPS while you're driving through the forest, and maybe someone's spoofing you other times when you're going through the forest.
Yeah.
How do you know where you are and where you're trying to go?
You really don't.
Okay.
You really don't. You have to start using other localization systems.
Like what?
LiDAR scan matching, optical flow from cameras.
Yep. And like all of that is stuff that like we can do where if we have a GPS coordinate we think we're getting to, we can find our way through the forest doing optical detection. If we get sufficiently lost or sufficiently off track, we can make our way back to where we started and try again. We can just keep on doing that over and over until we, get through the woods and to the house made of candy with Hansel and Gretel.
Yeah. And to the oven.
Yeah. Oh, geez.
The old Hans Christian Andersen stories.
On that note, Ilia, what are we going to talk about next week?
I'm not sure. Maybe come visit us at CES.
Yeah.
One more time.
So who knows if we'll get a podcast out before the holiday break or not, but we will be at CES. Come to our booth. We're in the automotive hall, I think. North Hall. We're in the North Hall with a lot of automotive stuff. We'll be demoing some robots. We'd love for you to come and check them out. And yeah, maybe we build some robots there or something.
Maybe we discuss Santa Bot next time.
Yeah, we really got to do a Santa Bot Christmas episode. Maybe that's next week.
That's right.
All right. Now we have to do a podcast next week. It'll have to be released for the break. All right. On that note, thank you all so much for joining us.
See you next time.